What is time? Definition of time. Time is a complex and multi-faced concept that allows us to understand and qualify the sequence of events and the progression of existence. It serves as a framework within which all phenomena occur, marking the duration and order of events. As its core, time can be viewed as a continuous, irreversible progression that encompasses the past, present, and future. While we often consider time to be a straightforward measure of hours and minutes, its implications are far more profound and intricate. Here are some common terms of time along with their abbreviations. BC, before Christ. CE, Common Era. BCE, before Common Era. AD, Anno Domini. YOL, Year of Our Lord. M, Millennium. C, Century. D, Decade. Y, Year. MTH, Month. W, Week. D, Day. H, hour. MIN, minute. S, second. Number 1, BC, before Christ. Before Christ, BC, is a traditional designation used to label years in the Gregorian calendar that occurred before the estimated birth year of the Jesus Christ. This system counts backward from the year 1 AD, Anno Domini. For example, the year 500 BC occurred 5 centuries before Christ's birth. The BC designation is primarily used in the Western cultures and is often seen in historical contexts, such as the Roman Empire fell in 476 BC. Number 2, Anno Domini, AD. Anno Domini, Latin for in the year of our Lord, is used to denote years in the Gregorian calendar following the birth of Christ. The abbreviation AD precedes the year number, for example AD 2024. This system was established by the monk Dionysius Exiguus in the 6th century and has been widely adopted in Christian-dominated societies. The usage of AD emphasizes the significance of Christ's birth in history and reflects the religious context in which the calendar was developed. Number 3, Common Era, CE. The term Common Era, CE, is a secular alternative to AD, used to refer to the same period in the Gregorian calendar. CE is often used in the academic, scientific, and interfaith contexts to avoid religious implications. For example, instead of saying AD 2024, one would say 2024 CE. The Common Era begins with the year 1 CE and includes all subsequent years, promoting inclusivity in discussions involving diverse cultures and beliefs. Number 4, Before Common Era, BCE. Before Common Era, BCE, is the secular equivalent of BC. It designates years before the start of the Common Era, 1 CE, and counts backward similarly. For instance, 500 BCE represent 500 years before 1 CE. BCE is preferred in academic and historical writings to provide a non-religious perspective while maintaining clarity in timelines. Number 5, Circa, C. The term circa, abbreviated as C. means approximately and is used in historical contexts to indicate that a date is not precise. When one writes C. 2000 BCE, it suggests that the event or period occurred around that time, allowing for some leeway in exact dating. The use of circa acknowledges the limitations in historical records and the uncertainty surrounding specific events. Number 6, Millennium. A millennium refers to a period of 1000 years. In the context of the Gregorian calendar, it is often used to discuss significant historical milestones or transitions, such as the turn of the millennium from the year 1999 to 2000. The concept of a millennium is significant in various cultures, religious, and scientific discussions, as it marks a large span of the time. Number 7, Century. A century represents a period of 100 years. In the Gregorian calendar, centuries are numbered sequentially. For example, the 20th century includes the year of 1901 to 2000. Centuries provide a convenient way to group historical events, trends, and developments, making it easier to analyze and discuss periods in history. Decade. A decade is a period of 10 years. It is commonly used to describe specific time frames, such as the 1980s or the Roaring Twenties. Decades are often associated with cultural, social, and political trends that define those years, providing a convenient way to categorize and discuss changes over shorter time spans. Number 9, Year, Month, Week, Day, Hour, Minute, Second. These terms denote the basic units of the time measurement. A year consists of 365 days or 366 in a leap year. A month varies from 28 to 31 days, a week has 7 days, a day has 24 hours, an hour has 60 minutes, and a minute has 60 seconds. These units are standardized and form the foundation of timekeeping in modern societies, enabling scheduling, planning, and organization. Conclusion: understanding these terms is essential for studying history, engaging in academic discourse, and navigating timelines effectively. The evolution of timekeeping systems reflect the interplay between culture, religion, and science, shaping how societies perceive and record their histories. The timekeeping methods. There were many timekeeping methods in the history, but here are some important timekeeping methods. Number 1. Sundials, the ancient solar timekeeper. Number 2. Water clocks, the flow of time. And number 3. Mechanical clocks, precision in timekeeping. Number 1. Sundials, the ancient solar timekeeper. Introduction. The sundial stands as one of the earliest non-timekeeping devices, with its origin dating back to ancient civilization such as Egypt and Mesopotamia around 1500 BCE. The principle behind the sundial is simple yet ingenious. It measures the time based on the position of the sun in the sky, utilizing shadow cast by a stationary object. As one of the first methods humans used to track the hours of the day, sundials were integral to the development of societies, facilitating agriculture, religious practices, and daily activities. How sundials work? A sundial consists of two primary components: the gnomon, a vertical stick or pointer, and the dial, a flat surface marked with hour lines. The gnomon casts the shadow onto the dial, and as the sun moves across the sky, the position of the shadow shifts. The length and angle of the shadow change with the sun position, allowing the observer to estimate the time of day. The dial is calibrated with marks or numerals to indicate specific hours, often dividing the day into 12 or 24 segments, depending on the system used. Sundials are designed according to the geographical location where they are placed, with the gnomon typically angled parallel to the Earth's rotational axis. This alignment allows the sundial to compensate for the Earth's tilt and rotation, providing a more accurate measure of time throughout the year. Historical development and types. Ancient Egypt and Mesopotamia. The earliest sundials were simple devices, often using a vertical stick planted in the ground to cast shadows. The Egyptians were among the first to refine this basic design into a more structural tool. Around 1500 BCE, they developed obelisks, tall, slender stone structures that acted as a massive sundials. These obelisks were not only timekeepers, but also religious monuments, symbolizing the connection between the sun, god, Ra, and the pharaohs. Greek and Roman innovations. The Greeks further refined the sundial concept, making significant contribution to its design and accuracy. Anaximander, a pre-Socratic philosopher, is often credited with introducing the concept of the gnomon to Greece. The Greek astronomer Eratosthenes later used a sundial to estimate the Earth's circumference, showcasing the tool's scientific potential. The Romans, borrowing from Greek innovations, spread the use of sundials throughout their empire. They placed sundials in public spaces, allowing citizens to track the time of day. The hemicycle, invented by the Roman mathematician Berosus, was a particularly popular design. It featured a half-bowl shape with a gnomon placed at the center, casting a shadow onto curved hour lines. Islamic advancements. During the Islamic Golden Age, 8th to 14th centuries, scholars further advanced sundial technology. Astronomers such as Al-Biruni and Ibn al-Shatir made significant improvements to the accuracy of sundials by refining the geometry and mathematical calculations used to construct them. Sundials were also used to determine prayer times, particularly the 5 daily prayers in Islam. Renaissance and modern refinements. In Europe, during the Renaissance, interest in science and astronomy led to the further refinement of sundials. Artists and scientists began constructing more intricate sundials, often adorning them with decorative elements and placing them in public squares and gardens. The invention of portable sundials made it possible for individuals to carry timekeeping devices with them. By the 17th century, sundials had become highly accurate, capable of marking the hours, minutes, and sometimes even the seconds of the day. Types of sundials. Sundials come in various forms, each tailored to the specific environments and purposes. Some of the common types of sundials include horizontal sundial, vertical sundial, equatorial sundial, polar sundial, portable sundial. Number 1. Horizontal sundial, the most familiar type where the dial lies flat on the ground and the gnomon is perpendicular to it. This is often found in gardens and public spaces. Number 2. Vertical sundial. Mounted on a vertical surface such as building wall, these sundials are common in urban settings where space is limited. They often have angled R lines to account for the position of sun. Number 3. Equatorial sundial. This type features a dial aligned with the Earth's equatorial plane. The gnomon is parallel to the Earth's axis, allowing the sundial to function accurately in any season. Number 4. Polar sundial. In this design, the dial is perpendicular to the Earth's axis and the gnomon is parallel to it. This type of sundial works best in the polar regions, where the sun's position in the sky changes drastically throughout the year. Number 5. Portable sundial. Designed for personal use, these small devices were often used by travelers. Some featured built-in compasses to help align the sundial correctly with the cardinal directions. Limitations of sundials. Despite their widespread use and historical significance, sundials have inherent limitations. Number 1. Dependence on sunlight. Number 2. Seasonal variations. Number 3. Geographical dependence. Number 4. Time zone discrepancies. Number 1. Dependence on sunlight. Sundials only work when sun is visible, making them useless at night or during cloudy weather. Number 2. Seasonal variations. The apparent movement of the sun changes with the season due to the tilt of the earth axis. As a result, sundials require adjustments or recalibration to maintain accuracy throughout the year. Number 3. Geographical dependence. A sundial designed for one latitude may not work properly at another location. The angle of the gnomon must be adjusted to align with the Earth's axis, which varies depending on the observer's latitude. Number 4. Time zone discrepancies. Sundials measure solar time, which varies depending on the observer's longitude. This means that the time displayed by a sundial may differ from standard time, which is based on time zones established by human conventions. Sundials in modern world. Although sundials have been largely replaced by mechanical and digital clocks, they still hold symbolic and aesthetic value. Many public spaces and gardens feature decorative sundials, serving as a reminder of humanity's long-standing relationship with the sun and the passage of time. Sundials are also used for educational purposes, helping students understand the concept of astronomy, geometry, and Earth rotation. In recent years, some enthusiasts have even developed modern solar-powered sundials, which combine traditional design with contemporary technology. These devices use sensors to track the sun's movement and provide a digital readout of the time, bridging the gap between ancient timekeeping methods and modern innovations. Number 2. Water clocks, the flow of time. Introduction. The water clock, also known as the clepsydra, is one of the oldest timekeeping devices, dating back to the ancient civilization such as Egypt and Babylon around 16th century BCE. Unlike sundials, which relied on the sun's position, water clocks measured the passage of time based on the consistent flow of water from or into a container. This innovation allowed people to track time indoors during the night and in various weather conditions, making it a significant advancement in early timekeeping technology. How water clocks work. The basic design of a water clock involves a container filled with water that either slowly fills or empties at a steady rate. The water level is marked to indicate specific intervals of time. There are two primary types of water clocks. Number 1. In-flow water clock. Water is allowed to flow into a container from a reservoir at a constant rate. As the water level rises, it passes marked intervals that indicate the passage of time. Outflow water clock. Water is stored in a container with a small hole at the bottom, allowing the water to flow out at a consistent rate. The decreasing water level is used to measure time. Some advanced water clocks feature mechanical components such as gears, dials, and automata, mechanical figures to improve accuracy and display the time in a more visual manner. Historical development and significance. Ancient Egypt and Babylon. The earliest known water clocks were used in Babylon and Egypt around 1600 BCE. Egyptian priests are believed to have developed the water clock to track the time during religious ceremonies. The priest could ensure that rituals were performed at precise moment, aligning with the movement of celestial bodies. These early water clocks were often simple devices made from stone or clay, with a hole at the bottom, allowing water to flow out. As the water level dropped, time passed and the priest could monitor the intervals for various ceremonial tasks. Ancient Greece and Rome. Water clocks became more sophisticated in ancient Greece, where they were used for both practical and legal purposes. The Greek astronomer Stabius 285 to 222 BCE is credited with improving the accuracy of water clock by incorporating mechanical components such as gears and floats. His designs allowed for a more consistent flow of water and more precise time measurement. In ancient Rome, water clocks were used to regulate legal proceedings. Lawyers were allotted a specific amount of time to present their cases, and water clocks were used to ensure that the time limits were adhered to. This practice highlighted the importance of time in Roman society. In ancient Rome, water clocks also played a vital role in regulating public speaking and legal proceedings. The legal system had strict rules on how long individuals could present their arguments, and water clocks, known as clepsydras, were used to measure these time limits. Public debates, speeches, and trials were often time-bound, and water clocks ensured that time was allotted fairly, highlighting the societal importance of time management. One of the most famous Roman water clocks was the Horologium of Augustus, a large sundial and water clock hybrid built in 10 BCE by the Emperor Augustus in the city of Rome. It showcased the sophistication of Roman engineering and timekeeping by combining solar and hydraulic elements to provide accurate time measurement for the public. Islamic Golden Age contributions. During the Islamic Golden Age, 8th to 14th centuries, scholars and inventors made significant advancement in the design and use of water clocks. The famous inventor Al-Jazari, who lived in the 12th century, designed elaborate water clocks with complex mechanisms. One of his most famous designs, the elephant clock, was not only a timekeeping device, but also a symbolic representation of cultural diversity, as it incorporated elements from various civilizations, including Indian, Egyptian, and Greek cultures. Al-Jazari water clocks were highly innovative, using a combination of water flow, gears, and levers to create automata, mechanical figures that moved in sync with the passage of time. These clocks were not only functional, but also served as impressive displays of technological ingenuity in palaces and public spaces. His contributions laid the groundwork for future developments in mechanical timekeeping devices. Medieval Europe and the Renaissance. Water clocks continued to be used throughout the medieval period, particularly in monasteries where monks used them to regulate prayer times and daily activities. In some cases, water clocks were combined with bells to signal the passage of time, helping maintain strict schedules for religious observances. In Renaissance Europe, water clocks became more sophisticated, incorporating advances in mechanical engineering. Artists and scientists during this period sought to improve the accuracy and functionality of timekeeping devices. By the 16th century, water clocks were increasingly being replaced by mechanical clocks powered by springs and weights. However, water clocks remained in use in certain parts of the world and were appreciated for their simplicity and reliability in environments where more complex mechanisms were impractical. Types of water clocks. Water clocks came in various designs, with some tailored for specific purposes. The most common types of water clocks include outflow water clock, inflow water clock, mechanical water clock, public water clocks. Number 1. Outflow water clock. In this type, water flows out of a container through a small hole at a constant rate. As the water level drops, the time is measured by the changing water level. This was one of the earliest designs used in ancient civilizations. Number 2. Inflow water clock. In this variation, water flows into a container at a steady rate. Time is measured by the rising water level. The inflow water clock was particularly popular in ancient Greece and Rome. Number 3. Mechanical water clock. In the Islamic Golden Age, inventors like Al-Jazari incorporated mechanical components into water clocks, such as gears, floats, and automata. These clocks use water to power mechanical movements, making them more accurate and visually impressive. Number 4. Public water clocks. Large-scale water clocks were often placed in public spaces, such as markets or town squares, where they served both a functional and decorative purpose. These clocks were used to announce the time to the public and were often designed with on-rate features, including moving figures and musical elements. Limitations of water clocks. While water clocks were a significant advancement over sundials, they had several limitations: inconsistency in water flow, maintenance, limited time range, vulnerability to environmental factors. Number 1. Inconsistency in water flow. One of the primary challenges with water clocks was ensuring a consistent flow of water. Factors such as temperature, water pressure, and the size of the hole in the container could affect the flow rate, leading to inaccuracies in time measurement. Number 2. Maintenance. Water clocks required regular maintenance to prevent clogging and ensured that the water flowed smoothly. Any blockage or irregularity in the flow could lead to significant errors in timekeeping. Number 3. Limited time range. Water clocks were limited by the amount of water they could hold. Once the water ran out in the case of outflow clocks, or the container filled up in the case of inflow clocks, the clock would need to be reset manually, making it less convenient than later mechanical clocks. Number 4. Vulnerability to environmental factors. Water clocks were vulnerable to environmental conditions such as freezing temperatures, evaporation, and contamination. In cold climates, water could freeze, rendering the clock inoperable, while in hot climates, evaporation could reduce the accuracy of the device. Impact on society and timekeeping. Despite their limitations, water clocks had a profound impact on early timekeeping and society. They allowed for the measurement of time indoors and during the night, providing a more versatile solution than sundials. This flexibility made water clocks essential for a wide range of activities, from religious rituals and legal proceedings to daily life and scientific experiments. Water clocks also played a crucial role in the development of more accurate and reliable timekeeping methods. The desire to improve the accuracy of water clocks led to the exploration of mechanical engineering principles, which eventually paved the way for the development of mechanical clocks in the Middle Ages. In addition, water clocks were a symbol of technological and intellectual achievement in many ancient and medieval cultures. They represented the human desire to understand and control the passage of time, a pursuit that has driven innovation for centuries. Water clocks in modern times. While water clocks have largely been replaced by more advanced timekeeping devices, they still hold a special place in the history of technology. Modern water clocks, often built as public art installations, pay homage to the ingenuity of ancient civilizations while incorporating contemporary design elements. For example, the water clock of the Swiss Pavilion at the 1964 World's Fair in New York was a large scale. Modern water clocks that demonstrated the continued fascination with water-based timekeeping. Similarly, in some cities around the world, water clocks are still used as decorative features in public spaces, serving as a reminder of the long history of human innovation in the field of timekeeping. Number 3. Mechanical clocks. Precision in timekeeping. Introduction. The invention of the mechanical clock in the Middle Ages marked a significant leap forward in timekeeping technology. Unlike sundials and water clocks, which relied on natural phenomena such as the movement of the sun or flow of the water, mechanical clocks used gears, springs, and escapements to measure time more accurately and consistently. The development of mechanical clocks was a crucial milestone in the history of timekeeping, leading to the eventual standardization of time and the creation of modern clocks and watches. How mechanical clocks work. At the core of mechanical clock is the escapement mechanism, which controls the release of energy from a power source, usually a wound-up spring or a weight, to drive the movement of the clock's hands. The escapement regulates the release of energy in precise intervals, allowing the clock to measure time accurately. The basic components of a mechanical clock include: Number 1. Power source. In early mechanical clocks, the power source was typically a weight suspended on a cord or chain. As the weight descended, it provided the energy needed to drive the gears and move the clock's hands. In later clocks, a coiled spring replaced the weight as the primary power source. Number 2. Gears. The energy from the power source is transferred to a series of gears, which reduce the speed of the movement and divide the time into seconds, minutes, and hours. The arrangement of gears ensures that the clock hands move at the correct rate. Number 3. Escapement. The escapement is a key component that regulates the release of energy from the power source. It allows the gears to move in small, controlled increments, ensuring that the clock measures time accurately. The most common type of escapement in early mechanical clocks was the verge escapement, which used a rotating wheel and pallets to control the movement of the gears. Number 4. Pendulum. In the 17th century, the invention of the pendulum by Christian Huygens revolutionized mechanical clocks. The pendulum swings at a constant rate, providing a highly accurate way to regulate the movement of the clock's gears. Pendulum clocks became the standard for accurate timekeeping until the development of quartz and atomic clocks in the 20th century. Time. Philosophical perspectives. Philosophers have long debated the nature of time, grappling with questions about its existence, its relationship with space, and its perception by humans. The distinction between absolute time and relative time is a critical point of contention. Sir Isaac Newton proposed the idea of absolute time, which exists independently of any observer, while Gottfried Wilhelm Leibniz countered with the notion of relational time, emphasizing that time is a system of relationships between events. Another significant philosophical perspective is found in the work of Henry Bergson, who posited that time is not merely a series of moments, but a flowing experience, which he termed duration. In contrast to the quantitative measurement of time, Bergson emphasized the qualitative aspects of our temporal experiences, suggestion that our perception of time can vary based on context and emotional state. Scientific understanding of time. In modern physics, time is treated as a dimension, akin to spatial dimensions. Albert Einstein's theory of relativity fundamentally altered our understanding of time. According to this theory, time is not a constant but is affected by factors such as velocity and gravity. As an object approaches the speed of light, time slows down for that object relative to an observer at rest. This phenomenon, known as time dilation, challenges our intuitive notions of time and suggests that it is intrinsically linked to the fabric of universal itself. Mathematical representation. In mathematics, time is often represented as a linear continuum, with the past represented by negative values, the present as 0, and the future by positive values. This linear model allows for the modeling of motion and change in a structured way. In advanced physics, time is treated as a variable in equations that govern motions, energy, and even quantum mechanics. When was time first registered? The concept of time has existed for millennia, but the formal recording and measurement of time began with ancient civilizations. The development of timekeeping system reflects humanity's growing understanding of the cosmos and our place within it. Ancient civilizations. c. 3000 BCE. The Sumerians, one of the earliest known civilizations, developed a sophisticated numerical system based on the number of 60. This base 60 system is still reflected in our measurement of time today. As we divide an hour into 60 minutes and a minute into 60 seconds, they utilize sundials and water clocks to track time during the day. Number 2. Egypt. c. 1500 BCE. The ancient Egyptians made significant advancement in timekeeping. They built sundials to measure daylight hours and water clocks to track time at night. The division of the day into 24 hours originated from their observations of celestial bodies, reflecting the importance of astronomy in their culture. Number 3. Babylon. c. 1800 BCE. The Babylonians further refined time measurement by developing a lunar calendar that divided the year into 12 months, each with 29 or 30 days. This calendar played a crucial role in agricultural practices, allowing farmers to plan their planting and harvesting cycles according to the seasons. Number 4. China. c. 1000 BCE. Ancient Chinese civilization also developed timekeeping devices, including water clocks and astronomical instruments. The Chinese calendar, which is lunisolar, reflects the interplay between solar and lunar cycles and is still in use today for cultural festivals and traditional events. Number 5. Greco-Roman contributions. c. 400 BCE. Ancient Greek philosophers such as Aristotle contemplated the nature of time, while others, like Archimedes, created water clocks that enhanced the accuracy of time measurement. The Roman adoption of the Julian calendar in 45 BCE introduced a more structured approach to tracking time, establishing a calendar year of 365.25 days. The medieval era and mechanical clocks. Number 1. Medieval advances. c. 1300 CE. The introduction of mechanical clocks in the late 13th and early 14th centuries marked a pivotal shift in the timekeeping.
These clocks allowed for more accurate measurement than previous methods, leading to the establishment of standardized time in cities and towns. Number 2. Astronomical clocks. During the Renaissance, advancement in astronomical knowledge led to the development of intricate clocks that not only measured time but also tracked celestial movements. These clocks often displayed the position of the sun, moon, and planets, reflecting the intertwined nature of time and astronomy.
Modern time measurement. Number 1. Standardization. 19th century. The advent of railroads and telecommunication in the 19th century highlighted the need of the standardized timekeeping. Sir Sandford Fleming proposed a global system of time zones in 1879, which was later adopted at the International Meridian Conference in 1884. Number 2. Atomic clocks. 20th century. The development of atomic clocks in the mid-20th century revolutionized time measurement. These clocks are based on the vibration of atoms, especially cesium atoms, and provide an unprecedented level of accuracy. The definition of a second was redefined in the 1967 as the duration of 9,19,26,31,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Number 3. Leap seconds. To account for irregularities in the Earth's rotation, leap seconds are occasionally added to the Coordinated Universal Time (UTC). This practice ensures that atomic time remains in sync with astronomical time. What are the kinds of time? Understanding time involves recognition its different kinds, each with unique characteristics and implications. Here are few kinds of time: physical time, psychological time, biological time, geological time, cosmological time. Number 1. Physical time. This refers to measurable time, quantifiable using instruments such as clocks and calendars. Physical time is objective and serves as the basic for scientific measurements and calculations. Number 2. Psychological time. Psychological time concerns how individuals perceive the passage of time, which can vary greatly based on context and emotional state. For example, time may feel slower during moments of boredom or distress and faster during enjoyable experiences. This subjective experience is influenced by attention, memory, and emotional engagement. Number 3. Biological time. Biological time encompasses the natural rhythms and cycles that govern living organisms. These include circadian rhythms, which regulate sleep-wake cycles, and other psychological processes based on environmental cues such as light and darkness. Biological time is crucial for maintaining health and well-being, as disruptions can lead to various health issues. Number 4. Geological time. Geological time refers to the vast time scales over which geological and biological processes occur. This perspective is essential for understanding the Earth's history, evolution, and the formation of geological features. The geological timescale divides Earth's history into eons, eras, periods, and epochs, encompassing billions of years. Number 5. Cosmological time. Cosmological time is concerned with the age of the universe, which is estimated to be approximately 13.8 billion years since the Big Bang. This time scale is crucial for understanding the evolution of galaxies, stars, and other cosmic phenomena. Cosmologists study time in relation to the expansion of the universe and the eventual fate of all cosmic structures. What are the types of time? Time can also be categorized in various types, reflecting its applications in different contexts. Number 1. Clock time. Clock time is the standard measure of time used in daily life, represented by hours and minutes as displayed on clocks. It is a uniform system that facilitates coordination in social and economic activities. Number 2. Solar time. Solar time is based on the position of the sun in the sky. It varies with geographic location and is typically divided into equal hours. Solar noon, when the sun reaches its highest point in the sky, marks the midpoint of the day. Number 3. Sidereal time. Sidereal time measures the Earth's rotation relative to distant stars rather than the sun. It is primarily used in astronomy and is approximately 4 minutes shorter than solar time. Sidereal days are used to coordinate observations of celestial objects. Number 4. Universal Time Coordinated (UTC). UTC is a time standard that serves as a basis for civil timekeeping worldwide. It is not subject to time zones
and is adjusted with leap seconds to stay in sync with the Earth rotation. UTC is the standard against which all other time zones are defined. Number 5. Greenwich Mean Time (GMT). GMT was historically used as the world's time standard based on the mean solar time at the prime meridian in Greenwich, England. While UTC has largely replaced GMT, the terms are often used interchangeably in everyday language. Number 6. Relative Time. Relative time refers to the notion that time is not absolute but dependent on the observer's frame of reference. This concept is foundational in the theory of relativity, which demonstrates that time can vary based on velocity and gravitational influence. Number 7. Local Mean Time. Before the standardization of time zones, local mean time was used to indicate the mean solar time at a specific location. Each community had its own local time, leading to discrepancies across regions. What is a time zone and how does it differ? A time zone is a region of Earth that has the same standard time, which allows for the synchronization of activities across different geographic locations. Time zones are defined by their offset from Coordinated Universal Time (UTC). Understanding time zones. Number 1. Geographic considerations. Time zones are generally based on the lines of longitude. The Earth is divided into 360 degrees of longitude, and since the Earth rotates 360 degrees in approximately 24 hours, it rotates about 15 degrees of longitude every hour. This division allows for a 1-hour difference between adjustment time zones. The prime meridian, 0 degrees longitude in Greenwich, England, serves as the starting point of the defining time zones. Number 2. Standardization. The establishment of time zones aim to standardize timekeeping across regions, particularly with the expansion of railroads and telecommunication in the 19th century. Before standardized time zones, time was kept locally, leading to inconsistencies and confusion. The widespread adoption of rail transport made it necessary to synchronize schedules across vast distances, promoting the need for a more organized approach to timekeeping. Number 3. Daylight Saving Time (DST). Some regions implement Daylight Saving Time (DST), adjusting clocks forward by 1 hour during warmer months to extend daylight in the evening. This practice was first proposed by Benjamin Franklin in 1784 and later adopted during World War I and II to conserve energy. While DST aims to make better use of daylight, it has also sparked debates regarding its effectiveness and impact on health and productivity. Number 4. Political and cultural factors. Time zone can also reflect political boundaries and cultural practices, leading to variations even within small geographic areas. For instance, some countries may choose to adopt a different time zone for economic reasons or due to historical ties. In some cases, regions within the same country may have different time zones, such as the United States, which has multiple time zones from east to west. Number 5. Irregular time zones. Not all time zones are uniform. Some regions have offsets that are not whole hours from UTC. Some countries may adopt time zones that do not correspond to their geographic locations due to political or historical reasons.